he'll be talking about neutral meson oscillation in the 331 model.
Okay, so thank you very much. I have short time to explain, so this will be somewhat superficial. I hope you enjoy. So I am Patricio, as Gaby said, and I work in Paraíba, in João Pessoa. And this work is a result of some research that we do with João Paulo Pinheiro, which will also present here in this gathering, and Professor Dov from Paraná, and also Professor Pires from the UFPB in João Pessoa. Okay, this is published in the Journal of High Energy Physics. Okay, let's go. First, there is a common belief that the phenomena of meson oscillations requires ultra heavy C prime in the 331 model. Okay, so the idea originally proposed by Professor Pires is that that is not the case, and you should study this situation in a more systematic way. Okay, so the spoiler is the following. I will try to explain this plot along the presentation, and now I just want to emphasize that the lower limits can be weakened as low as 400 or 500 GeVs. Okay, so those limits are at reach from for the LHC in its current form. Okay, and that's a novelty as we showed. Okay, so what are neutral meson oscillations? Are meson anti-meson transitions. That's it. So a meson is walking on the street and has an identity crisis and becomes its antiparticle during propagation, and then becomes the particle, antiparticle, until finally it decays, right? So we are interested in electrically neutral mesons with non-trivial flavor configurations. For instance, we are not interested in neutral pions, okay? Why? Because anti-neutral pion is a neutral pion, it's the same, okay? So we are interested in other kinds of mesons. And famously, these processes are forbidden, or more generally, flavor changing neutral currents are forbidden at tree level in the standard model. This is the Glashow-Iliopoulos-Mayani mechanism. And the meson and the anti-meson do not have well-defined masses, okay? So a linear combination of those is what have well-defined masses, and a splitting is induced for those degrees of freedom. We call those degrees of freedom the short-lived and the long-lived. And by the way, one is CP odd and one is CP even, so CP violation has a lot to say in this context, but let's forget about that for this presentation, right? Okay, so which mesons are we actually measuring? 4 of them, okay? 3 of those mesons, which are bound states of a quark and antiquark, are the K meson, the BD meson, and the BS meson. And interestingly enough, the top quark decays before any hadronization process can happen. So those mesons are not realized in the lab, okay? So we have just one meson formed by upright quarks. That's the D one, okay? So it's kind of special. And let's look at the process itself. So what happens? In a collider setup, a strongly interacting particle is produced, a quark or a gluon, and it hadronizes and starts to propagate. Among all the possibilities of hadronization, some of them turn out to be neutral ones, of the 4 that I presented just before. And okay, this meson starts to propagate, and as I said, it has an identity crisis. So meson anti-Meson. Black and white, Corinthians, Palmeiras. It's an identity conflict, okay? And this process is induced by flavor-changing neutral currents. And there are two time scales important for these processes, which are the decay time scale and the oscillation time scale, okay? These scales are not related. They belong to different realms of physics, to different sectors of the Lagrangian. So we hope that are comparable or suited for our needs in for experimental purposes, you see? Okay, so the time scale of the decay, it has to do with what channels are open, okay? And the time scale of the oscillation has to do with flavor changing neutral currents. And the time scale of the oscillation is obviously inverse to the frequency of oscillation, and this frequency is proportional to the mass splitting that I just presented before of these long and short-lived degrees of freedom, right? So roughly, what happened? Okay. So roughly, we have three situations, okay? So the meson can oscillate a lot before decay, or can oscillate 1 or 2 times before decay, or didn't even have time to oscillate until it decays, okay? So I hope it's clear to you that have a lot of oscillations is a statistically better setup for experimental measures. So better measurements are realized in that direction, okay? And the result is the following. The D meson, the special one, the only one formed by up quarks, is the most difficult to measure, and therefore it has a greater error band, okay, like 11%. And the other ones are very much better measured, you see? So our approach is that the central values of these mass splittings or these frequencies of oscillation are consistent with higher order standard model contributions. The Glashow-Iliopoulos-Majani mechanism says 3-level flavor changing neutral currents are forbidden, but at 1 loop level or higher, you have these processes. And for instance, that one, okay, but you need to be careful because there are non-perturbative effects in the hadronization, in the formation of these mesons. But for our work, we just said that the new physics lies on the error bars, okay? So what is the new physics? So this is somewhat technical part of the presentation. I hope it's clear to you. Let's look at this expression, but let's first talk about the 331 model. The 331 model is a model in which the weak isospin gauge group is promoted from SU2 to SU3. And in doing so, you introduce more gauge bosons, more scalars, a different pattern of symmetry breaking. It's a whole story. You can have neutrino masses and different variants. It's a big model, but we expect to see somewhat similar in nature, for instance, for grand unified theories or other classes of models. Okay, let's look at this expression now. This is not working. Okay, so the Yukawa interaction will mediate these processes of flavor changing neutral currents at 3 level, and that's a novelty. Okay, what we have here, we have some mixing angles, that those are kinetic mixing angles among the scalars, the Higgs sector of the model, and we also have these matrices, BU and BD, which are quark mixing and represent the flavor structure of the model, and they are constrained to factorize into the CKM metrics. These matrices BU and BD are not experimentally accessible, but the CKM is. So we have infinite solutions, infinite choices of quark mixing that reproduces the CKM results. And on the other hand, other characteristic of this interaction is that the mixing angles of the scalar sector allows for a suppression of flavor changing neutral currents. Okay, so if we choose this particular setting, the Higgs just not mediate Meson oscillations, and we call that the alignment limit of the scalar sector of the 331 model, in clear analogy with the alignment limit of the two Higgs doublet models, but the two Higgs doublet model has a minus sign in this relation, so we found a fundamental difference, challenging the belief that you can embed one model into the other. Okay, so on the other hand, you also have gauge contributions to Meson oscillations, and if you do the math, you can derive this mass splitting, or this frequency if you want. And let's look at this expression. You have a factor of the Fermi constant, the Weinberg angles, okay? And you have the ratio over there of the traditional C boson over the new C boson. And you have the pion decay constant, the pion back parameter, which is a non-perturbative quantity calculated with lattice techniques. And you have the mass of the particular meson. And you also have a renormalization group factor that allows us to calculate a next to leading order. But the important thing here is the middle one, the quark mixing matrices. Now, why is a 3 over there? That 3 is the materialization of the fact that in the 331 model, because of anomaly cancellations, you need to put one family of fermions transforming differently than the other ones. You have a triplet, and an anti-triplet. Which family of fermions? It's your choice, but there are hierarchy arguments to choose the third one. But to be objective, you need to explore all possibilities. We call that the variance of the 331 model. Okay, so our procedure goes like that. We consider the alignment limit, the suppression of the scalar sector, and infer lower bounds on the mass of the C prime for a given quark mixing pattern. Remember, the quark mixing pattern is just constrained to give the CKM phenomenology, but you have infinite solutions. So as good physicists do, we try the trivial ones first. And interestingly enough, the trivial ones are the extreme solutions. Let me explain. In the first scenario, we consider just the responsibility given to the up-like quarks. So we infer just D Meson oscillation. And remember, the D1 is the special, the only one formed by up quarks, and the less known, okay? The difficultest to measure. So that is the least restrictive case. And in the first column, you can see our result that the key BD and BS oscillations are absent, but the D1 is present, and it represents a lower bound very weak compared to the one given by the LHC, which is about 4 TeV. And in the other hand, in the second scenario, we give all of the responsibility of Meson oscillations to the D quarks. So, the down-like quarks. So the D Meson does not oscillate, and the other 3 ones do. So we infer stronger bounds, like ultra-heavy C boson, and that's the common situation in the previous literature. Okay, so let's look at this graph again. In the vertical axis, you have the contribution of C prime to the error bands in Meson oscillation as a function of the mass of the C prime. And the horizontal line represents the alignment limit when the scalar sector does not contribute. If you go down in this plot, you are going out of the scalar alignment limit, and you are giving responsibility to the Higgs to Meson oscillations, giving less room for C prime, and therefore the constraint becomes stronger and stronger. And if you are above this horizontal dashed line, you're completely excluded. That's not in agreement with experiment. So the scenario 1 is the scenario with the D oscillation, just up like Meson states. And the green one is the other scenario in which we applied these Meson oscillations to the D quarks, the down-like quarks, or mesons, okay? And we consider also a third scenario, which is mixed, right? And our claim is that the lower bound can be in any spot in between these two extremal scenarios. Okay, so these are my conclusions, and I'll be happy to answer your questions. Thank you.
Thank you very much. Questions?
Thanks, Patricio. Really nice talk. So for example, how can you justify having just the D meson oscillating, which is your scenario? Because the other mesons do oscillate, right?
Yes, yes. And the central values are, as I said, attributed to the standard model phenomenology. But that's a good question, because that means you are treating your errors in a different way for each meson. So I think that's the lower possible scenario, but if you did consider all of that, you will have a weaker bound, a lower bound in between.
So you're just assuming that, let's say, as you said, the VU,
right,
is just CKM, and
right,
the other is the unit.
The unit.
And then the others one don't oscillate, and they just go to the one which has the weakest limit. Right?
Yes, yes, that's represent like
which is, let's say, is in reality it would be like a more, say, how could I say? It's tricky, right? To have two matrices, one being precisely the unit, and the other one being precisely the CKA matrix.
Yes, yes. That's why we claim that when we have experimental access to this flavor structure beyond the CKM, we will try to adjust our procedure more and more. But you're right, that's a tricky procedure. Yes. And in fact, for instance, in previous works, they just consider, for instance, BS oscillations, and arrive at these conclusions that the C prime should be ultra heavy. So our claim is not that the C prime is lighter or heavier than some particular value, is that how the flavor and the scalar mixing structure really can modify in a dramatic way this thing. So
I get it.
that's it.
Okay.
But I get it, it's tricky. I mean, you need sophisticated procedures to address what you just said.
But anyway, it means that, for instance, you set the limits, right? The weakest limit and the strongest limit, which is the one which is the inverse, right? The down quarks, the down quark mesons give rise to the strongest constraints, which is above 100 TeV.
Yes. Yes. Yes.
But including the Higgs, it just worsen the scenario, right?
Yes. Yes.
Because you have little room for the Z prime.
And in fact, you also have other scalars contributing. We just decouple that, assuming that they are very heavy, but in principle, their presence will also strengthen these lower bounds.
But for instance, did you compute the scalar contributions to the Meson oscillations or no? Did you contribute the scalar contributions or no?
Yes, yes, we calculate that.
And they are weak, they are smaller than the Z prime one, right?
Right, and yes, yes, they're
So
weak.
in the end,
And in fact, it can be negative, so
but anyway, so the presence of new scalars, summing all of them up, are they sizable compared to the Z prime or much smaller?
are sizable when the masses are compared. The principal, the main...
The masses being similar, let's say, the masses, all of them being similar.
Yes, because they are proportional to the inverse mass squared, because this is a tree level and you have just one propagator, so...
But one has a Yukawa, the other doesn't.
Yes. Yes, the pseudoscalar doesn't, right? So...
Yeah.
Yes, in this work we just decouple them. We assume that they are very heavy, but in a complete future work they should be included. Yes.
Okay.
And they're sizable.
Sorry, we don't have more
problem,
time
no
for questions. I'm sure Patricio will be happy to discuss later. Let's take him again.